Okay, thank you everyone for being here. Thank you, Jacques, for being here. We have yet another talk. This is the fourth term now in the 2021 Stellenbosch year. And today, Jacques will be talking about incidence geometry. He's been in Stellenbosch from 2016, I believe, where he was introduced at some stage by near vector spaces, actually by Dr. Howell. And then he got very into it and he just went on with mathematics and so on. And he's at a stage now where he's busy with his master's, but he got it upgraded to PhD, which I don't know how often you can actually do that, but I think it's quite an achievement to do that. And one of the main reasons maybe is because he solved an open problem that was open from 2015, and it was about I don't even know, also near vector spaces, but which is quite cool. So yes, thank you very much, Jacques, for being here, and you can go ahead.
Thank you, Rocco. I think of the people in the audience, you may be the only one who hasn't seen the problem before. It was about subspaces of near vector spaces. So vector spaces are subspaces of vector spaces are closed under addition and scalar multiplication, or rather any set that's closed under addition and scalar multiplication. Non-empty subset of a vector space is a subspace. And essentially I was able to prove that for near vector spaces as well, which I did using some of the geometry I'm going to talk about now. Okay, so hello everyone. I'm going to talk a bit about incidence geometry, geometry without length, angles, or continuity. So this is all very exciting. And I think we'll start where we are all with what we're all familiar with, the Euclidean plane, and sort of build up from there, or rather maybe build it down from there, since we're stripping it of length and angles and continuity. So let's look at the axioms. So the Euclidean plane has 5 postulates, right? These are Euclid's postulates or axioms, and I guess everyone who is in this meeting would know what an axiom is, but if anyone else watches it later on, an axiom is basically just the rules for maths is just a game, and the axioms are the rules of the game. So in the Euclidean plane, you can draw a straight line from any one point to any other point. So this is a very natural idea. Finite straight line segments can be extended continuously in straight lines on both sides. Very normal, nothing too weird about that. Given a finite straight line segment, one can draw a circle whose radius is the segment and whose center is one end of the segment. This is also nice, although maybe not what we're looking for when we're talking about geometry without length or angles or continuity. I mean, a circle is just all points in the plane a certain distance from another point. All right angles are equal to one another. That seems self-explanatory. And then if a straight line falls on two straight lines, makes interior angles on the same side whose sum is less than two right angles, then the two straight lines, if extended continuously, meet on that same side. And I say yikes, this is not Euclid, because this definition or this axiom seems a bit complicated at first glance. It was in fact thought to be provable by the first 4 by very many mathematicians for very many years. I gave a talk recently where I mentioned the mathematician Muhammad al-Khwarizmi. He tried to give a proof of it. His proof involved movement, though, something that you don't really have here, and so it was really a bit invalid. But let's look at what this axiom really means. So we've got a straight line lying on two straight lines, and the interior angles on the one side sum to be less than 2 right angles, or less than 180 degrees. Then if these two lines are extended continuously, they will meet on that same side. Now, it may not be entirely clear why this is immediately, but if we were to take the axioms as they are, Euclid's postulates, we would be able to show that this axiom is equivalent to saying, given a straight line and a point, there's a unique straight line that does not intersect this one. Okay, so that's a bit nicer, right? We don't have to talk about angles at all. We don't have to talk about extending straight lines or whatever. We can just take some straight line, right? And then there is, and some point, and then there is a unique straight line that does not intersect this one going through this point. Now, this is what Euclid uses to define parallelism. So these two lines are now what we call parallel. Okay. So something that maybe I didn't mention is that these postulates are only really useful or nice when you know what points, straight lines, and circles actually are. And Euclid tries his best to give definitions for these concepts, but it's kind of complicated to do so. And Euclid isn't very successful. For example, his definition of a point is that of which there is no part. I don't know about you, but that doesn't necessarily make sense to me. And whatever we want to say about points is, well, even if it did make sense, giving a negative definition for something isn't really describing what it is necessarily. It doesn't get any better. For example, a straight line is just a straight line is any line on which lies evenly, a straight line is any one which lies evenly with points on itself. And I don't know about you, but I imagine a circle to have points that lie evenly on it. And a circle isn't necessarily or really a straight line. I guess depending on which geometry you work in, a straight line can be a circle. So these definitions, the definitions need a bit of work, and the postulates are also a bit complicated if you don't know what the definitions are. But if we agree that the concepts are more or less understandable as they are, then these postulates can lead to a lot of interesting maths. And in fact, so important or so fundamental that up until at least the late 18th century, no, the late 19th century, it was expected of very learned people to have read and studied Euclid's Elements. So yeah, well, it's all very interesting, and it has led to a lot of new mathematics. In particular, incidence geometry. And incidence geometry says, okay, what happens when we remove from normal geometry notions of continuity, length, and angles? What if all we're left with is which points lie on which lines? Okay. And I think what I'm going to do is I'm going to go for probably the most natural one of these geometries, the affine plane. Now the affine plane is what you get when you strip the Euclidean plane of everything but its incidence structure. So in everything but what points lie on which points lie on which lines. So an affine plane is a geometry of points and lines satisfying the following three conditions. Every 2 points are incident with exactly one line. This is exactly as in Euclid's first postulate. The parallel axiom, if we have a line G and a point X that's not on G, then there is exactly one line H through X that has no point in common with G. And as I mentioned earlier, this axiom is equivalent to Euclid's fifth postulate without needing any concepts of angle or without needing the concept of angle. So it's a nice substitute there. And then lastly, every line is incident with at least 2 points. There are at least 2 distinct lines. These are sort of natural assumptions to make, that we have 2 points on the line at least, and that there are at least 2 lines. If there were only one, we wouldn't imagine the resulting geometry to be a plane, really. We just think of it as a line itself. Okay, so let's try and prove something with this. So I say every line in an affine plane has the same number of points. Okay. Think about it. We've got 2 lines. How can we prove that these 2 lines have the same number of points? These 2 lines may intersect, they may be parallel. We don't particularly care. We just want some way to show that these 2 lines have the same number of points. So the sort of natural way of proving this is taking 2 points on each line and joining them by a line, right? So here we are applying our first axiom, or maybe let's start with we're applying the third axiom, in that each of these lines has at least 2 points, so we can take at least 1 point from each of them. And because these lines are not equal to each other, because they're not the same line, we can take 2 distinct points from them. Now we can join them with a line. This is the first axiom. And then we sort of make this function going from the one line to the other, where we take all the parallel lines parallel to these and sort of pair up the points from one line to the other that we pair up the points that exist on these intersections of these parallel lines with these lines. There's a bit of detail here, but it should be relatively clear that we can do this. Now we've got a function going from one line to the other. It's injective because if 2 of these lines meet in the same point, then they can't be parallel because they meet, right? It's also surjective because you have a line going from each point back towards this one, right? So it is a one-to-one function. It's onto, and so it's invertible, which means there's a bijection between the points on this line and the points on this line, and that tells you that they must have the same number of points. And what we do then is we call the number of points on each line the order of the line. So in an affine space of order n, each point is incident to n+1 lines, and n+1 lines, there are n squared points and n squared plus n lines. So maybe let's examine this statement. Why do I say there each point is incident to n plus 1 lines. Well, take a point, right, any point, and take a line that is not incident with it, right? That line has n points on it, and we can therefore join each point on that line to our original point that we started off with. So that gives us n lines, and then there's an additional line that's parallel to the one that's not on our point, incident to our point, and so we get n plus 1. There are n squared points. This is maybe a bit more complicated to show. Yes, and n squared plus n lines, also a bit more complicated to show, but basically we get some geometry that has, if we've got an affine space of order n, we get these sort of combinatorial results from that. Another thing we have, what we would like, is that every finite affine space has prime power order. So far, every single known affine plane that we know, every single affine plane that we know of has some prime power number of points on each line. For the most part, this is due to the fact that we can sort of make affine planes from vector spaces over finite fields, and then the order of each line is the order of your underlying field. But there are some planes that, or affine planes, that aren't generated by fields. And I'm going to show you an example, the Moulton plane. What the Moulton plane does is each line in the Moulton plane is, maybe let me start off with, the points are just the normal points in R2. Your lines, however, are all normal except for the lines with negative slope, and these lines, when they reach the y-axis, their slope doubles. So you can see here the slope is -0.5, and here it's -1. Here the slope is -1, and here it's -2, etc. So this is also, surprisingly, an example of an affine plane. Parallelism works exactly as you would expect it to work. And there's a unique line joining any 2 points. So it's very interesting, but very unexpected, but you do get affine planes that are sort of weird like this. And these types of planes, what we call non-Desarguian planes, are not generated by fields. Okay. So the next thing I would like to talk about is a generalization of the affine plane. If we want to work in 3D space or 4D space or whatever, we would need this, the affine space. And what are the axioms of an affine space? Once again, every 2 points are incident with exactly 1 line. There's some parallelism, and here parallelism is an equivalence relation on the lines of A such that the condition for parallelism holds, the standard one from a bit earlier. And any plane of A is an affine plane. So any plane of A, 2 lines are parallel if and only if their intersection is non-empty. And lastly, every line of A is incident with 2 points. There are at least 2 lines. So what's a bit strange about what's a bit different about the parallelism axiom is that now we don't assume that there's a unique line such that if we've got a point X and a point and a line L, then we don't assume there's a unique line G such that G and L don't intersect. If you would, if you want, you can imagine in R3 two lines that don't cross each other, that sort of run in different directions. So what we really want here is for parallelism to encode that two lines run in the same direction. Okay, so that's why we have this. If we don't have the third axiom, some weird things happen. We can get lines that are parallel that sort of are sticking out of planes, but we don't want that. So we add the third axiom just to ensure that any what we call two-dimensional subspace of A is an affine plane. Okay. So some interesting counting or combinatorial results here are that there are n to the d points for a d-dimensional affine space. I haven't talked about what that means, what dimension means in this case, but you can sort of create a set of points, take a set of points and generate a subspace from that set of points. So you can take all the lines between those points and sort of from there generate a subspace by taking all the lines parallel to those and continuing so on and so forth. And if you've got d plus 1 of those points, then you've got a d-dimensional affine space. Okay, and so we've got on a d-dimensional affine space into the d points and into the d minus 1 times into the d minus 1 over n minus 1 lines. If you were to go back to how many points and lines are in the affine plane, you would see that this holds there as well. And we also have some good news about the affine space. Any affine space of dimension greater than or equal to 3, so anything that's not an affine plane, is also a Desarguin. So we don't get any weird things. And all the ones with dimension greater than or equal to 3 are sort of generated by d-dimensional vector spaces. So that's nice. Yeah. Now let me talk a bit about my own work, the near-affine space. So the near-affine space is sort of a generalization of the affine space, in which the points and the line joining two points together depends on the order in which you join them. So there's this. So this is the definition. It's quite long, and there are many axioms. But this joining function here, taking pairs of different points to lines, is not necessarily commutative. So what do I mean by that? So we have something like this. Here we've got x join y, right? X is sort of central to the line. It is the point around which the line is symmetric. And y is the point on the line that gives it sort of direction. So if you were to imagine, if you were to take any other point on the line other than y, you would generate the same line. But x is sort of important. It's what we call the base point of the line. So when I said this joining function is non-commutative, I meant that x join y is not necessarily equal to y join x, and you can see it in this case. Here you have x join y and y join x, two different lines. Once again, y is the line y join x is sort of symmetric around y in a special way. But what you will also notice is that these two lines are sort of translations of one another. So if you were to move this line on top of this line, then you would get two lines that are, then you would get sort of the same shape. So we just move the one to the other. And that's nice. That's what we use in this geometry to encode parallelism. And that's always very nice. And in general, we always have that x join y is parallel to y join x, even if they're not equal. Now we've talked a lot about, I've shown a couple of geometries now where we haven't had length or angles. Maybe I should do justice to this one and say that you don't necessarily need continuity. This is, the lines in a near-affine space can look like this, but they can also look like these hyperbolic functions where x join y is sort of this hyperbola which is centered, which has center x and some point y on it, and y join x once again is centered around y. So even though x and y aren't what we would imagine to be on the lines, they are still incident to them. So y, this line y join x still is incident to y, even though we don't see like a continuous line going through it. Okay, so you do sometimes get that x join y is equal to y join x. In that case, there's no sort of central defining point on our line, and that is what makes our line straight. So yeah, in this case, this line is straight. There's no central defining point. If you had another point z on it, then it would also be equal to z join x or z join y. Okay, and that is basically it from my side. Thank you. If you want, I can also talk a bit more about what I did for my proof of the subspace problem. And I have a couple of slides on that from a different presentation. Yeah, thank you. So subspaces of near-affine spaces. So subspaces of near-affine spaces are defined in a way that sort of makes sense for them. For any 2 points x and y in your subset of a near-affine space, the line x join y is contained in it. So lines are sets of points. So you can sort of find the whole line x join y in U. The second one is a bit more complicated. So if x, we require that x and y are joinable in U. So the reason we have this condition is because we want sort of straight in a standard near-affine space. There's sort of a sequence of straight lines from any one point to any other. So what that means is we've got this P0 to Pn of points, such that the line Pi minus 1 join Pi is straight, going from x to another point, any other point. Now we require that also to be also to hold in a subspace of a near-affine space. So we would need this joining sequence to also be in U. Okay. So This is a nice definition. It's a full definition, but the second condition isn't very nice under things like intersection and things like that. So if you were to imagine taking two subspaces, U and U prime, then their intersection, if x join y is in U, is a or if x and y are in U, then x join y is, if x and y are in U and in U prime, so they're in the intersection, then the line x join y is in U and it's in U prime because both of them are subspaces. So the whole line x join y is in U intersected with U prime. For this condition, it's not necessarily as clear whether it holds, whether it's stable under intersection, which is sort of a kind of central problem to figuring out these subspaces and in turn understanding the near vector spaces corresponding to them. So what Andre does sort of to remedy this is he defines a weak subspace. So in this case, x join y, we just have to satisfy the first condition. So that's nice because now we can take the weak subspace generated by a set of points as the intersection of all weak subspaces containing it. So we can sort of generate a weak subspace from any set of points. Okay. What Andre was able to do, though, with subspaces was sort of build upon them by adding an additional straight line. So if you want, you can imagine taking a straight line, and adding a new straight line, and those two can generate a plane. And if you add a straight line to that, it generates the whole of 3D space, if that makes sense. So that's on what Andre does here. Basically, he takes the subspace U and he takes all lines parallel to your given straight line G with what we call base points Y. So Euclid's axiom is also sort of brought in here. Okay. So first result that I was able to show was that, well, the first big thing was that the subspace U comma G is equal to the weak subspace generated by U union G. And this is assuming that G intersects U in a point. The first direction is relatively clear because U union G is a subset of this subspace. It must be the whole subspace or weak subspace generated by it must be contained in it, in this one. The reason for that is this is the intersection of all weak subspaces, and that includes subspaces that contain the union. The other direction is a bit less clear, but I have now not included the proof in this discussion, but it does hold. You sort of build upon a proof with straight lines using a sequence of parallelograms. So it turns out weak subspaces are in fact subspaces. So you can sort of drop the second condition and still end up with a subspace. And the proof is by contradiction. It took me very long to do, I think about 6 months on and off. Since when was it? Up until May of this year. So yeah, December to May about. So the outline is as follows. It's proof by contradiction. So we assume we have some near affine space with a proper weak subspace, so one that isn't a subspace. And then we are able to show that there's some finite dimensional subspace U containing a proper weak subspace. And this is very useful because now we can make arguments, minimality arguments, without having to worry about things like infinity. Step 2 is doing exactly that, making some minimality argument. Take U to be the subspace with smallest dimensions such that U contains a weak subspace. Then we take X and Y in U with minimal joining sequence in U. So what that means is, if you remember, there's a straight line joining sequence from X to Y, at least one, for any 2 points X and Y in U. So what we do is we take the X and Y such that their joining sequence is the shortest it possibly can be, such that they aren't joinable in the weak subspace generated by them. The reason that there must exist some weak subspace, that there must exist some pair X and Y such that they aren't joinable in their weak subspace, is if we have a proper weak subspace, that means there are at least 2 points without a joining sequence between them, so they aren't joinable, right? What that means is that the weak subspace generated by them is contained in that proper weak subspace, right? Because these 2 points are contained in the proper weak subspace. And it follows from that X and Y can't be joinable in the weak subspace generated by them because they're not joinable in the larger proper weak subspace containing it. Step 4 is showing that the dimension of U is exactly equal to the length of the shortest joining sequence from X to Y. Now we take some basis for U through X. So in this case, in a nearaffine space, basis consists of straight lines. So what I mean by straight lines generate a nearaffine space is that we can that we've got this underlying structure of straight lines going helping us along. So we've got this basis of straight lines through of straight lines in U, all intersecting in X. So what we show is that the weak subspace that's the intersection of the weak subspace X, Y intersected with this. So the subspace generated by G1 through Gn minus 1. So we're leaving out the nth line, is a strong subspace. This should be relatively clear. We assumed that U is the subspace with smallest dimension such that it contains a proper weak subspace, and S is contained in this subspace that's in -1 dimensional. So consequently, S must be a strong subspace, because if it were a proper weak subspace, it would contradict that initial idea. So the next bit was sort of the hardest bit, or the point where I was stuck for very long, is showing that S contains more than just one point. So we want a straight line G in S, and if we are able to show S is more than one point, because S is a subspace, it's got a joining sequence between those 2 points, so there must be at least one straight line in S. Okay, so this step 6 breaks up into 2 parts, but I've got sort of a visual proof for one of them. Step 7, now that we've got this straight line, I'm just going to finish before I show you the proof. now that we've got a straight line G contained in S, contained in the weak subspace SY, contained in U, we've got G in the weak subspace, right? And that's important, that we have a straight line contained in our weak subspace. So now what we do then is we build a path from Y to a point Q on G of length less than or equal to n minus 1. I'm glossing over the details here a bit, but you basically take a basis for U, a basis for U going through Y instead of through X, but you build it up from the line parallel to G going through Y, and then you sort of arrive at a point Q, which is less than or equal to n minus 1 straight lines away from Y. And because of the minimality condition on the joining sequence, or the minimality condition on X and Y, that they are the points with shortest joining sequence in U, such that they are not joinable in the weak subspace generated by them, we can conclude that Y and Q, because they've got a shorter joining sequence, they must be joinable in the weak subspace generated by them, also in the weak subspace generated by X and Y. Okay, but now we are able to conclude that X and Y are joinable in X, Y. Why? Because Q and Y are joinable in the weak subspace generated by X, Y, and X and Q both lie on G, so the joining sequence from X to Q is just the straight line G. And so we arrive at some joining sequence from X to Y, and that is the contradiction. Okay. The step 6 that I was talking about, we've got X and Y. We want to show that S, which was the weak subspace generated by X and Y, intersected with the subspace generated by the lines G1 through Gn minus 1. That was more than a point. So what we do is, okay, first off, note that X join Y is not equal to Y join X. If it were, the line would be straight and the weak subspace generated by X and Y would just be that straight line. So we have something a bit more complicated than this, just a straight line, but that's okay. That's good, in fact, because now we can take some point Z that's on X join, which is on X join Y, but not on Y join X. Now the line Y join Z either runs parallel to the subspace generated by G1 through Gn minus 1, or it intersects it in a point. In the latter case, it's relatively easy to show then that S is more than one point. But in the case where Y join Z runs parallel, that took a bit longer and was a bit more complicated. So what we do here is we take the line through X parallel to Y join Z, with base point X parallel to Y join Z, and we take some point X prime on the line. What we need to show is that X prime is contained in the weak subspace generated by X and Y. So it may seem sort of obvious in the sketch, but remember that this doesn't need to happen in like a planar setting, nor do we need continuity of our line. So it can be a bit more complicated than it seems. So we note that these two lines are parallel to each other. So we are able to apply one of our axioms called the Tomashka axiom to get that these two lines have non-empty intersection at a point W. And we now know that X prime is on Z join W, right? So if we can show that this line Z join W is contained in the weak subspace generated by X and Y, then we are done essentially, because X prime lies on the line. So we've got Z on X join Y, we've got W on Y join X. So naturally both points must be in the weak subspace. And so the line generated by them must also be in the weak subspace. And finally we get that X prime must be in the weak subspace. And that is a lot of work to arrive at the conclusion that one subspace is more than just one point. Okay.